Right, in this session we're going to start looking at probability. Probability is a way that mathematicians measure chance or likelihood, how likely something is of occurring. So we'll start off really basic with the sort of F and G type of questions, and then work our way up to the sort of grade C and B questions. So probability is measured on a scale between 0 and 1, where 0 is impossible and 1 is certain. And probabilities can be written as fractions, decimals, or percentages. So we need to be able to use or work with probability if they're given in any of those three forms. There are occasions when you can't quantify, when you can't put a number to a probability, but you can use language. So the language that is associated with probability in maths would be certain, very likely, likely, even chance, unlikely, very unlikely, and impossible. For example, there would be other ones as well. So a very basic sort of GCSE question, or one you would have met probably back in year 7 when meeting probability for the first time, would be to put words like that against statements like the ones below. So what would be the probability it will rain in Tenby in August? Well, it's not certain, but I would suggest that most years rain will fall in Tenby at some point during August. So I would say very likely, or maybe likely, would be the most appropriate there. B, the probability that a person chosen at random from a class is left-handed. Well, in every given class you will have individuals that are left-handed, but there'll be far more right-handed students than left-handed. So if I was to walk into a classroom in school and just pick one person at random, there's a much greater chance that person would be right-handed than left-handed. So you would probably say unlikely that I would pick that left-handed person. When I roll an ordinary dice, it will have a score less than 7. Well, an ordinary dice has the numbers 1 to 6. All of those numbers are less than 7, so it would be certain. Okay, so certain, not certain. If I select a card at random from an ordinary deck of playing cards, it will be red. Well, I'm sure you know that on an ordinary deck of playing cards, which has got 4 suits, diamonds, hearts, clubs and spades, half of them are red, the diamonds and hearts, and half of them are black. So there'd be an even chance. You'd be equally likely to get a red or a black. If I win a prize in a raffle, which has sold 1,000 tickets, and I've bought 1 ticket, well, I've got the same chance of winning as everybody else, but it's equally unlikely. I would say it would be very unlikely. It's not impossible, but it would be very unlikely. Another thing they like to get you to do at the easier end of GCSE is to mark things like that on the probability scale. So you can see there the scale goes from 0 to 1. So halfway would be where evens, less likely, more likely. So very likely it's going to rain in Tenby in August means you're going to put it up there somewhere. Now it's not exact, but it's going to be closer to 1 than to halfway. The person chosen at random from a class is left-handed, unlikely, probably about there. Certain for the dice, so that's C, will be on 1. D is an even chance, so that would be exactly in the middle. And very unlikely would be down pretty close to 0. So that's a really basic entry into probability. As I said, it's the way you'd have been introduced to it back in year 7. And it's unlikely that you would get a question like that on an intermediate tier paper. Events C, D and E above can be written as numbers. So we're now entering a more useful form of probability where we can write them in numerical form. So C, when I roll an ordinary dice, it will have a score less than 7. So the way that we write a probability is generally as a fraction, and on the bottom of the fraction will be the possible number of outcomes. Well, when you roll a dice, you could get a 1 or a 2 or a 3 or a 4 or a 5 or a 6. There are 6 possible outcomes, and all 6 of them are less than 7. So the number on top is the number of occurrences that meet the probability. And the other thing to say here is when we talk about probability, I know I'm talking about a probability because the way that it's written. P tells me it's probability, and then what's in brackets is explaining what we're measuring. So C, so this is the probability when I roll an ordinary dice, it will have a score less than 7, 6 out of 6, or 1. Probability of D. So when I select a card at random from an ordinary deck of playing cards, it will be red. There are 52 cards in a deck, and half of them will be red. So you could write that as 26 out of 52, or you could have written it straight down as a half, or 0.5 or 50%. And then the last one, I will win a first prize in a raffle where it's sold 1,000 tickets and I've bought 1. So the number of possible outcomes are 1,000, and I've got 1 of them. So you can see that that's going to be a very small number. Now this, I can't really do this online because I don't have you all in front of me as far as the class is concerned. But if we change B to say a person chosen from this class, then we can also write this as a number. So there are 28 of you in our class. So the probability of choosing a left-handed person will be out of 28. If I ask the class to put their hand up, let's say 4 of you put your hand up to say you were left-handed, then that would give me the probability of 4 out of 28. Because total probability adds up to 1, okay, you can't have anything greater than 1, we can use this to find the chances of something not occurring. So for example, E. So that if the chances of me winning is 1 in 1,000, the chances of me not winning would be the difference between 1 and 1 out of 1,000, which is going to be 999 out of 1,000. So the chances of me not winning are the 999 tickets I don't have out of 1,000. And for B, the chances of that, if there are 4 out of 28 being left-handed, then 1 less 4 out of 28 is going to be 24 out of 28. So the chances of me not picking a left-handed person, well, there's 24 out of 28 in the room that aren't left-handed. Now we come into the sort of questions you're far more likely to get in intermediate tier, but still down at the sort of D, E area. So sometimes information has been put in a table. So here's the example. Number of paper clips in each of 40 boxes was counted. The results are summarized in the following table. Now what I will encourage you to do, which I do with all the students I teach, is if you are presented with a table, make sure that you understand what that table is telling you by picking a column. So let's say I pick that column there. I want to turn that into a sentence. So the top row is telling me the number of paper clips. So 23 in a box, 24 in a box, 25 in a box, 26 in a box, 27. The frequency, that's telling you how many times that happens. Now I know there are 40 boxes, so this is telling me that out of the 40 boxes, there are 13 boxes which contain 24 paper clips. Now once you can turn one of those columns into a sentence in the context of what the data is, it makes your understanding that much better and answering the questions that much easier. So this one, for example, would be saying out of the 40 boxes there are 10 boxes which have 26 paper clips in, and so on. So what is the probability that a randomly selected box of paper clips contains exactly 24 clips? So probability of exactly 24 clips, which is A, will be 13. There are 13 boxes out of the 40 which contain exactly 24. For part B, you need to have an understanding about what certain words mean in maths. So this is the probability of at least 25 clips. Well, for at least 25 clips, that means there could be 25 clips, but there could also be 26 or 27 clips, because all three of those will give you at least 25. So the probability of at least 25 clips would be those 14 and those 10 and that one box. So that's 25 out of the 40 boxes. An odd number of clips, so the chances of you getting an odd number of clips would be if you picked a box with 23 in, or a box with 25 in, or a box with 27 in. So that's going to be 2, 16, 17 out of 40 boxes available to you. And then fewer than 23 clips. Fewer means it doesn't include 23, it's less than 23. So the probability of you getting fewer than 23 is 0, because there aren't any boxes in that 40 that have got fewer than 23 in. So you would just write that as 0. So it's important that you can handle data given in a table. Okay, then we move on to listing possible outcomes. These come up again quite frequently on an intermediate tier paper, and you're pushing the DC boundary now. So when you're told that two events are happening together, for example, two coins are flipped, or two spinners with different numbers are being spun, then it will help to list all the possible outcomes before you consider the probabilities of something occurring. So if I've got a red four-sided spinner numbered 1, 2, 3, 4, and a blue three-sided spinner numbered 1, 2, 3, and they're spun together, what's the probability that the total score is 4? So what you need to do here is make sure that you have considered every possible outcome. So what we use here is what's called a sample space diagram. So we've got a red numbered 1, 2, 3, 4. So 1, 2, 3, 4, red, and blue numbered 1, 2, 3. And when they're spun, their scores are added. So that means that here we could have a blue one and a red one, and that would come to a 2. We could have a blue 1 and a red 2, so the 2 and the 1 are added. Then we could have a blue 1 and a red 3, or we could have a blue 1 and a red 4. So those are the possible outcomes with a blue 1. We could have a blue 2 and a red 1, which would add to a 3. A blue 2 and a red 2, a blue 2 and a red 3, and a blue 2 and a red 4. And then we could have 3 and 1, 3 and 2, 3 and 3, 3 and 4. So these are all the possible outcomes. So inside that table, or sample space diagram, as it's properly called, are all the possible outcomes. So in this game of spinning these two spinners, there are 1, 2, 3, 4, 8, 12 possible outcomes. So total score is 4. Will be out of 12. And then we want to see how many times we could get a score of 4. So we could get a score of 4 there by blue 3, red 1. Could get one there, blue 2, red 2. Or we could get one there, blue 1, red 3. So the chances of getting a total score of 4 is 3, because there are 3 ways you could score 4, out of 12, because there are 12 possible outcomes. And we could do the same thing when 2 fair dice are rolled. So I don't know why I've done this so small, but if you imagine we've got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Then when we roll the 2 dice, we could have a 1, 1, a 1, 2, a 1, 3, a 1, 4, a 1, 5, a 1, 6. So those aren't 11, 12. Okay, so on the first dice we got 1, 2, 3, 4, 5, 6. On the second dice we got 1, 2, 3, 4, 5, 6. So I could end up with a double 1, a 1, 2, a 1, 3, a 1, 4, a 1, 5, or a 1, 6. Then here I could get a 2, 1, a 2, 2, a 2, 3, a 2, 4, a 2, 5, a 2, 6. I could get a 3, 3, I could get a 4, 4, I could get a 5, 5, I could get a 6, 6. So these are all the doubles. So there's only one way I'm going to get a double 6. So there's only one way that will happen. And although I haven't managed to fit that in, hopefully you can see that what we're going to have here are the 6 outcomes, another 6 outcomes, all the way down to where I got a 6. So there's going to be 6, 6, 36 different outcomes that I could keep writing there. So just like here, where I've got 12 outcomes, because I've got 2 6-sided dice, that's going to give me 36, 6 sixes. There I've got 4 outcomes, 3 outcomes, 4 threes are 12. So what's the probability of not scoring a double 6? Well, we know that its total probability is 1. So it's got to be the difference between 1 and 1 out of 36, or 35 of those numbers inside that sample space aren't going to be a double 6. So 35 out of 36. P not 6, 6. So the probability of not scoring double 6 would be 1 less that, which is 35 out of 36. Sometimes you would be given a context where a table like that, like we just used, doesn't work as well. But it's really important that you're systematic and you control how you are writing your list. So we'll look at this example now, okay, which could easily be off an intermediate tier paper. My local Thai restaurant has the following lunchtime menu on Saturdays. Choose a starter and main, or main and dessert for £12. how many different combinations of food can I choose for my meal? So where students go wrong here is they just go mad and they say, well, I'm going to have a corn cake and a red curry. Oh no, I could have a yellow curry and rice, then I could have a satay and light cheese, and all of a sudden lose control and then don't know whether they've actually listed everything. So it's much better for you to be organized, and what you do is you fix what you can. So first of all, if we consider that we start with a corn cake, with my corn cake I could have choose a starter and a main, or a main and dessert. So starter and main could be corn cake and red curry. But keeping my corn cake as the starter, what other possible outcomes could I have? Well, I could have a corn cake with a yellow curry, and I could have a corn cake and a green curry. There's nothing else I could choose to eat with my corn cake starter. So now I've exhausted that, I change my starter and I have a fish cake. With my fish cake I could have a red curry. With my fish cake I could have a yellow curry, and with my fish cake I could have a green curry. Nothing else. So then I change my starter. What if I have satay? Well, if I have satay starter, I could have a red curry. Satay starter, I could have a yellow curry. Satay starter, I could have a green curry. That's all the possible lunches I could eat if I'm having a starter. But I could have a main and dessert. So we do the same thing now, but this time we fix the main and we consider the dessert. So with my red curry, I could have light cheese. With my red curry, I could have a pineapple fritter, or with my red curry, I could have rice. So now I know that I've got all the possible meals if I go for a red curry main. Once I've exhausted that, I then move on to yellow curry. I could have yellow and light cheese. I could have yellow and pineapple fritters. I could have yellow and rice. Can't have anything else, but I could have a green curry starter, main course. I could have green and light cheese, green and pineapple, green and rice. And because I've been systematic, organized in how I've listed my outcomes, I know I've got them all. That's an exhausted list. So how many different combinations of food can I choose? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 different combinations. What's the probability that I eat a red curry? So the chances of me eating a red curry, well, I could have gone starter and main, and then that would have been one, that would have been one, that would have been one. Or I could have had a red curry main with desserts, which would have been that one red, and that one red. So out of the 18, probability eat red curry will be 1, 2, 3, 4, 5, 6 out of the total 18 different combinations. So questions like this, which come up in the first half of the intermediate tier paper, are really easy marks so long as you're organised in how you list your outcomes. Sometimes the context of the question means you might discard some combinations. So it's the same as what we've just done, but the context changes. So Mr. Jones needs to choose a team of 2 to enter a maths competition. He's narrowed down the choice between Abigail, Brian, Colin and Debbie. Quite often in an exam question you'll see that the names are you can shorten to A, B, C, D, so you don't have to worry about wasting time writing down the whole thing. So list all the possible teams that could compete. Well, remember, we're going to be systematic. Team of 2. What if I have Abigail? I'm going to fix Abigail. She's in. Who could be with her? Well, Brian could be with her, or Colin, or Debbie. No other combination will include Abigail. But I could fix Brian. So I could have Brian and Abigail, Brian and Colin, Brian and Debbie. Or I could have Colin as my fixed team member, and I could have Colin and Abigail, Colin and Brian, Colin and Debbie. Or I could have Debbie and Abigail, Debbie and Brian, Debbie and Colin. So those are all the possible teams, but because it doesn't matter whether I've got Abigail and Brian or Brian and Abigail, it's the same team, I wouldn't be including them both. If I've got Abby and Brian, Brian and Abigail is the same team. If I have Abby and Colin, Colin and Abigail are the same team. If I got Abigail and Debbie, Debbie and Abigail would be the same team. Brian and Colin, I wouldn't have Colin and Brian. Brian and Debbie, I wouldn't have Debbie and Brian. Colin and Debbie, I wouldn't have Debbie and Colin. So when I'm listing my outcomes here, those are just repeats of those. So in fact, the total number of possible teams I could actually choose would be 1, 2, 3, 4, 5, 6. So I got Abigail and Brian, Abigail and Colin, Abigail and Debbie. Or I got Brian and Colin, Brian and Debbie, or Colin and Debbie. So what's the probability that Brian fails to make the team? No Brian. Well, there are 1, 2, 3, 4, 5, 6 possible outcomes, and of those 6, Brian isn't in that one, or that one. So 1, 2, 3. So there's a 50% or there's a half or 0.5 chance that the team isn't going to have Brian in it. So because of the context of that, we can discard those. But there are other instances where we can't. Okay? So if 2 coins are flipped, what's the probability that they both land showing heads? So, coin 1, coin 2. Hang on, just confuse things there. Coin 1, coin 2. So when I flip the coin, when I flip them both, the first one could come up heads, and the second one could come up heads. The first one could come up heads, and the second one could come up tails. So I fixed coin 1 being a head and considered the 2 possible outcomes for coin 2. Then coin 1 could be a tail, and coin 2 could be a tail, or coin 1 could be a tail, and coin 2 could be a head. So there are 4 possible outcomes. Probability, both land showing heads. So head, head. So the number of ways it could be a head, head, well, there's only one way, but it's one way out of 1, 2, 3, 4 possible outcomes. So that little chunk of work is all to do with being organized and systematic and careful when you are listing things which you are then being asked to get a probability from, as well as how to write the probability where you've got total number of possible outcomes on the bottom, the denominator, and the number relevant to your measure of probability at the top. And also, if I wanted to find out the chances of it not both showing heads, you do 1 minus a quarter, should be 3/4. So once you've got your head around that, have a go at the past paper questions that follow.